All right, so that we don't wait forever, I'll start recording right now, and let's go to our to the lecture. I hope the midterm is not too long. You got about 5.5 days, and if some for those of you who were asking, why am I closing the midterm at midnight instead of 1:30? So it's like a due date, and then the last day, the last time before you can submit. I realized that I don't want to put pressure on okay, I need to have a sharp 1:30 p.m. because I figure a few of you would ask me that, and it's Monday, so some of you, but it's Tuesday, so some of you have classes. So basically, if you submit after 1:30 p.m., but between that and the midnight of that day, it's fine. The midterm is designed already for, I was it 3 or 4 hours, and you got 5.5 days for that. So adding less than 12 hours to that, it doesn't matter. Okay. So it's not 3 or 4 hours for you. Okay. Then maybe I should give you more homework so that you get used to Scala uh, and so that you can answer those questions in 4 hours. Okay. So let's begin our lecture by resuming what we learned. So last 2 weeks, I know it's a long time ago, we've heard about something called parallel programming. We talk about future, we talk about the concept of running things together, running things concurrently, which to put in more like a hardware context, right? Because I love to go around like tangential topics and add things that are not related to the class then. But I think this helps with your understanding of parallel programming. How many of you buy a computer with a multiple core? And if you have a computer that's at least newer than 15 years ago, our computer will have multiple cores. So I think everyone here has a laptop or desktop with multi-core. Right? These days, you're looking at 6 to 8 cores depending on which one you're buying. If you buy AMD machines, sometimes you have 6 core, 12 threads. If you buy the Intel machines, you might have 8 core, 16 threads. If you buy a server, for some reason, if you're rich, then you might have 16 core, 32 core with 64 or 32 threads. Those threads are the hardware threads that allow you to run a multiple program at the same time. Basically, if you have YouTube open, if you have Chrome open, if you have Microsoft Word open, if you have 20 different Chrome tabs on your machine, right? They will basically, the machine will run up to that many threads at the same time. Wait, what's the question? How do we check again for? Is it for the exam? Sorry, I was confused by the question on the chat. The core. Oh, so I think if you right click on computer, like the computer button, or if you're in using Apple, Mac OS, you can click that Apple logo, and I think it's either system preference or about this computer or something along that line, and it would have the exact make of your processor. Basically, if you look at that process, like let's say it's i5 and some model name, you can Google that out. Yes, about this Mac, thank you. Yes, there's a button called about this Mac. And with that model number, if you Google that, you know exactly how many processing core do you have. So quad core Intels typically mean there are 4 cores. It might have more than 1 thread per core. These are hardware threads that are capable of running almost in parallel. If you would like to understand when I said almost in parallel, what's the difference between that and truly parallel, check out our computer architecture class because we're actually about to go into that topic next week after we talk about the main memory. But anyway, because I know one of you are in that class, or 2 of you are in that class. as well. So with that concept where you can run things in parallel, and with that, we talk about writing code that can run things in parallel. Today we'll go into, okay, let's look at what Rust can do and what's unique about Rust, which is a language that allows you to run things in parallel easily. I'm not talking about the fact that they can run things in parallel because a lot of languages can do that. What Rust allows you to do is to be honest, to make a safe parallel program, Rust is easier. Similar to Scala, they will always yell at you when you write a code and you try to compile it. It won't even allow you to run. Rust would behave the same way. When you compile and everything compile, everything should behave like the way you designed it to, right? And if you, by accident, decide to have bugs in your code, it will be running and with bugs on your code. So then we'll talk about the algorithmic aspect of parallel programming a little bit because we need to kind of discuss how the algorithm should look different to make the program truly parallel. We just need at least 2 core, right? That's a great question. Actually, you only 1 core is also okay. The interesting part about the operating system, now I'm talking about the operating system, which is Linux, Mac OS, or Windows, is they actually spawned this thing called software threads. Software threads allows you to actually have multiple things going on in parallel, and the operating system will pick which one get assigned to that specific core at that moment in time. So if you have only 1 core, let's say you have a machine back in the day, the Pentium 4, Pentium 3, basically you have 1 processing core, but you can still run Windows, and within the Windows you have what was over in the Windows back in the day? Like Paint, for example, Microsoft PowerPoint, Microsoft Word, right? And they'll all run. They'll make it as if you truly believe that everything there is being run together. So it doesn't matter if you have many cores or not, right? But it's better if you have more cores. If you have more cores, you can run more programs in parallel. Within the same program, right now we're talking about within this 1 program, you can actually run multiple tasks in parallel. But before we go through that, right, let's actually introduce what's unique about Rust. And what's unique about Rust is this thing called the ownership system. This is actually designed to make sure your memory is rather safe and fast, right? And if you took the system skill or file processing, this is probably like a 10th time I'm asking you this, but I'm sure you are sick of segmentation faults, right? So this ownership system keep track of the next possible bug that you can have. If you won't run into seg fault this time, you'd run into the case where someone modified the content of your data without you noticing. Let's say you run a bank, right? And 2 people try to withdraw money on an ATM on the same account, and it just happened that instead of withdrawing, say 1,000 baht for both of them, you only have 1,500 baht on your account. The only one should be able to withdraw. The other person should not be able to do that. The fact that you can have shared memory and the fact that you need to manage shared memory, if you do not do it well, the bank will allow both people to withdraw 1,000 baht. Then you have 500 baht back in the ATM, back in your account. Okay? So from your bank perspective, you need to make sure you do that really well. Otherwise, you lose money. So the ownership system keeps track of who else needs the data and share the memory. It will also determine when do I need the memory. This is an important aspect for performance. Why is that the case? How big is your DRAM that you have right now on your system, on your laptop? How big is your memory? Can some of you check it up and type it on the chat? Okay, 15.9 gigabytes. So let's say you have 16 gigabyte memory. You have, and you are more fancy, 20 gigabytes is kind of weird. What's your setup? Is it 8 plus 4 plus 4? You might have a kind of suboptimal, 4 is onboard. Yeah, this onboard memory is odd. Okay, so if you know how DRAM works, that setup is kind of odd. You might have allocation to the 4 gigabyte and it will perform different from the allocation that go to the 16 gigabytes in terms of bandwidth and how fast is the memory. So let's say you have 16 gigabyte of memory, and at some point I run so many programs. What do I have to do to make sure I don't run into the case I open so many Chrome tabs and my computer becomes slow and too slow to actually do anything? Well, if you are the user, you close down the tabs, right? If you are the program, one thing you can do is you free up the memory because basically at that point, memory is full. So the ownership system keeps track of who owns the part of that data. And if no one owns it, it means that you can free that data because no one needs it, right? So this is for performance. Basically, it allows you to tell when things become free. If things become free, it means you can free that thing right away, right? So the introduction of the ownership system allows you to have memory safety. It also allows you to have a really, really good way to keep track of what things can be run in parallel. So let's talk about the lifetime of a resource, right? So with the ownership system, what Rust would do is would go and look for, okay, when should I kill certain resources that you allocated? This can be done through what we call checking the scope. It checks the scope. This is the same scope concept that we learned from before midterm 1, right? The scope allows you to know what data is still alive and you need to keep and maintain the data. What certain other data is not alive anymore. No one needs it because no one can call and use the data. These techniques can be also done on the compiler. So if you have program in C, you can do this thing called liveness analysis. So I'll briefly talk about this during the compiler section, I think on the last lecture of this semester. We will not go on to the exam. I just want to kind of briefly introduce you now that we know about a bunch of languages. I'll briefly talk about what the compiler can do and so that you can see, okay, what goes into the compiler whenever I have the language. It tracks what resources that are free, and then when you know the lifetime ends, you free up the resources so that you can allocate the next set of resources. So here are some examples. Let's say you have this curly bracket and say let s equal hello, right? And you do something in the code. From this example, s is not the value until this line, right? Until this line, and it's no longer valid after this line. Any questions about this? This should be pretty self-explanatory. Whenever you define something, that definition becomes valid after that line. Then after you have this closed curly bracket, the scope ends, so S no longer becomes valid. So the ownership rule is pretty simple. Every single value will have one single owner. Let's say you buy a car. There should be only one owner to that car. Otherwise, if you have 5 owners and 5 of them want to use the car at the same time, they will fight and, well, I guess one emerge and you will be the single owner of that car. Why is this good? It it basically allows basically it allows the hardware, the computer system, and also the compiler to know that, okay, this is the process that owns the data. Then, when more than one person or more than one people or more than one processes want to use the resource, that is the value that you declare, they can borrow them. They don't borrow the value, they borrow the reference to the value, right? And this borrowing, let's say you borrow a car and the owner say, hey, I'm going to sell that car. The borrower cannot use the car after the owner sold the car, right? It means that if you borrow some reference, it should not outlive the value. It should not outlive the value. And to change the value, you need what we call exclusive access. What does exclusive mean in English? What does exclusive mean in a normal English? The only one, yes. So you need to have this special access type called exclusive access. You are the only one who can change the value at that instant of time. Who owns the exclusive access can change over time, but at any instant of time, there will be only one of them. And this is what we call the single ownership system, right? And here's some examples. So variables have their own values, right? And struct, for example, you declare struct that consists of integer, character, string, double, floats, whatever. They own their field. Allocated value on a heap. The heap, if you haven't taken the OS or system skill class, the heap is basically this growable part on your memory, on your DRAM, the memory stick that you buy or whatever people call the memory, right? It's a portion of that memory that you can allocate more things on it. Basically, it allows the heap to grow as you need more space for your program. The allocated value only has one single pointer that points to that value, that owns the value. If owner drop the value is dropped. Let's go to a string type, for example. There are two ways to represent the string. You can use the ampersand str or a more like a object style string, right? So what I can do here is I say let is similar to the def in Scala, right? So what does MUT stand for? Anyone still remember from 2 weeks ago? Yes, mutable. It's kind of like var in Scala. Basically, you let string that is float, right? And then this string is mutable. I have two questions. What's the type of hello and what's the type of s? Now that we know there are two forms of string, an actual str as a string or an object string. So what is hello? This is a pointer of string, right? It's a pointer to the string. And s is formed by creating this object called a string. So if you s, because string has this built-in function called push string, push string basically append, right? A literal, which is the ampersand str, it append world to the first word. So what you get is now hello world instead of just hello, right? Why is this okay? Why can we modify this? Because we already declare, right, that s is mutable. Do we need that comma? That's a good question. The answer is no. It's just a part of the string. I just want to be nice and have a pause between the word hello and world. I just want to say hello world instead of hello world. Print line is format like this: print line with the ampersand. Ampersand. My bad. Print line with exclamation mark, and inside you can do this bracket is similar to %s in C. Basically, this bracket tells, hey, whatever goes in here, look to the next argument. S. So it would basically print hello world. To copy the data, what are copying? Copying is something like this. I said let x equal y and then let y equal x. So this first, oh, what's the bracket for? This is similar to when you have printf %s. It's basically within the quotation when you see the bracket, it means that, okay, go look into the next input because that's where I want the actual things you want to print. S here is a string, so it means that I'm going to print the string, whatever S is containing right now. Right now it contains the word hello world. So you go into print line and say, I see this bracket, the bracket sees S has the value hello world, so it prints hello world. Does it answer your question? So what will happen if you do print line S? S. So I think print line take a literal string, which is the ampersand str. S is a string, so you might need to do the conversion, but it might have an implicit conversion. So I have not tested that. So my guess is it should also print hello world, but I'm not quite sure. Do we always need the exclamation mark after the print line? That's a great question. So if you do this, it would print as if it's print out. So yes. Interesting. The question asking the ampersand. No. Why do I always say the ampersand? Exclamation mark. Sorry. It's sort of similar to printf in Java and C. Yeah. All right. So let's continue on copying the data. Right. So over here, when you have this bracket that says let x equal 5, let y equal x. What this would do is it first bind the value 5 to x. Then when you do let y equals x, you actually copy x to y. Copy x to y. What if I do something like this? What will happen? It means that okay, let's focus on the first part, right? Where you have string called hello, and you really want to copy S1 into S2. If you do this on Rust will say use of move value S1. Use of move value S1. The reason behind this is more on because of the performance aspect of copying. When you have a string, for those of you who took system skill before, what does string copy actually do? What does string copy actually do? Let's say you have the first string x, right? Hello, right? And then now, right? So that you know the end of the string. And you want to copy x into y. What will happen is you literally copy each letter over here. E-L-L-O, right? This process takes some time. It's O of n, right? You need to copy each character. When you do S1 S2 equal S1, what happened in Rust is it's similar to C actually. To C, if you do this in C language, S2 is a pointer to the same location of S1. So let's say S1 is right here. Point to the string. What you do here is say S2 point to this location. What's wrong with this in Rust? What's wrong about this in Rust? Yeah, there should be only one reference to that location. So S2 is not supposed to own that. It's not supposed to point to that, right? And the integer part over here is okay because you first bind x to 5 and then you create an automatically copy x, oops, here, the value of x, which is now 5, right, into y. This is done implicitly because it's an integer, it's quick. It's quick. When you deal with the string, it's not as quick. So Rust doesn't assume that this is what you want to do. So they'll think that, okay, you're trying to assign S2 to the same location as S1. Okay, something is broken here. I'm going to yell at you and will not compile. This is not implement. Your copy is not implemented by default for a string because this is what we call deep copy. This is what we do here is called deep copy, and this is expensive because you need to copy each element, right? You need to go through everything, copy everything over. It's not only one single item anymore. So if you really want to perform the deep copy, which is what I draw earlier, use the word clone. Basically, this is how you do it. S2 is now equal S1.clone. What you get is S1 that has the string hello. And then you will clone. So this is S1.clone will return this, right? This new array, new string that contains the same exact word. And now you have two separate copy. So what we just saw is some data type have implicit copy. You can do S2, X equal Y equal Z if those are integer. If those are Boolean, floating point, character. If you have a tuple where everything inside is a copy type, then you have the copy trait. You can do this implicit copy. Otherwise, you either need to write your own function to do that or clone. So just be careful when you write things in Rust. If you want to do something like S2 equal S1 and it yells at you saying, use of move value as 1. This is what it means. You need to make a separate copy. If you still want to, same slide, my bad. So now, what if you want to call a function? Right? What if you want to call a function? In C or Java, right? Let's say you have int add, and you have int a and int b, and you return a plus b. This program in C, and you basically call add x and y, right? So right here on this line, who owns the value? X and y basically owns the value of x and y, right? But when you call that function, A and B takes whatever x and y's value are. So now you need to give the ownership to A and B because the variable A and B need to be able to be the owner to do something with it, right? So with the function call, this is what you can do. Basically, passing a value to a function is similar to how you assign things. Consider the example copy was smooth, right? So let's go through an example. So let me stop sharing right here. And then I'm gonna show the example code quickly. All right, do you see my screen that has the main function and the function called take ownership? Yes, no? Okay, awesome. So the comments to the right, I'm going to post this code after the class. So the code is basically doing something pretty simple. I have a main function that I declare a string called hello, and I allow whatever is inside here to take the ownership. This inside variable is called some string. Then you want to, then the other thing I'm doing here is declare a variable called x, and I make a copy. And this is a function called make copy. Again, I want to print something, right? When you talk about the scope, when you declare s come into the scope. With me so far? I32, so that's a great question. I32 is integer 32 bits, 4 bytes integer. It's an integer type, has sign, you can have a plus and minus portion of that integer, and it's 32 bits. Take ownership s. Basically, this allows s value to move into the function. So s now, at this point, s is no longer valid because the ownership is moved to some string. Some string comes into the scope, and then you print some string, which is hello. When you see this bracket right here, some is no longer valid. It goes out of the scope. Because no one used s over here, right? No one used s over here. You see that no one used s, right? So once this bracket ends, this bracket right here, s goes out of the scope. Right? S goes out of the scope. But because the ownership, right, the ownership of s already moved into the function, the ownership of s already moved into the function, nothing special happened for s because at that point it's already been deallocated. Now let's talk about x, the integer. Because notice that s doesn't have a built-in copy, right? So you are actually moving, not copying. Over here, when you have x as an input, you make a separate copy. X goes into this function. This some integer is a totally different copy than x. It has its own scope. It has its own value. You print that value, some integer no longer becomes valid right here, right? No longer become valid right here. But x is still viable after this point. You can use x afterwards. So the difference here is after this point, you move s into the function, s goes out of the scope. You can't use s. Over here, you make a copy for x. X is still in the scope. You can use x. See the difference? Nope. Okay. Remember from move versus copy, integer, when you do this kind of assignment, it make a separate copy. But remember, still remember our earlier example, where integer will make its own copy. For a string, unless you do s.clone, this is moving. Basically, you move s into the function called take ownership. The function called take ownership would use that string. S no longer owns that. S goes out of the scope, but since S no longer owns the ownership to the string hello, nothing happened because by the time you finish this function, you drop. You already drop the string hello. So that's a difference. Over here, you make a copy of integer. So when you go out of the scope, that particular copy gets dropped. But because it's a copy, you still have the original value x, right? So after this point, X is still active, so you can still use X afterward. So that's basically what happened here. Yeah, so for the first question is, as in basically over here, you define some integer that equal 5, and you make a copy which goes into that function called make copy, and you can use that. Yes. So for integer, for the second question, for integer you can use it many times. For string you can only use once unless you clone. So implicitly yes. The answer is yes. Because these are being cloned implicitly. When you make copy x, you pass x into the function. S dot clone. So basically instead of s, you do s dot clone. So the last question, this was asked also privately as well. So basically, what can we use in place of s to make a copy and not a move? S dot clone will create a new copy. That new copy gets passed to the function. The function takes the ownership. And would this run in parallel? No. The parallel library in Rust will cover that in next week. There are some fancy things you can do in Rust that would kind of like do things in parallel. If we were to call take ownership as a clone, then S will still be available. Yes, it should still be available because the take ownership function doesn't kill the value S. All right, so let's go back to here. So you see my slides. And these are good thing to watch out because then your code will compile properly. So I'm gonna post the example code onto your canvas. You see my screen now with the PowerPoint slide? Okay, awesome. So let's move here. So let's say I have this function called the main function, and I have a helper function named string. The ownership of name over here with the helper function, right? With that same example with s, right? You notice you already give the ownership to the helper function. You finish, so you kill the value already named. So when you use it, this violate the ownership rule. Okay. So this is a good thing to watch out. The difference, so let's summarize the difference between moving, cloning, and copying. Move means I'm passing a variable that things that cannot be copied around unless you forcibly clone it. Clone is basically it's a custom code that you make a copy. You define how you want to make a copy. The copying is more implicit. When you do x equal y, this is done implicitly. Now we know about the ownership system. Since it's 10:54, let's take a quick, maybe 5 to 10 minutes break. Let's meet at 11:05. Is that okay? And we'll continue on talking about borrowing. So the thing about string is not copying unless you explicitly say, hey, copy this. Because it's not copying, you move the ownership into the function call, so it goes out of the scope after the function call ends. And okay, so let's do a 10 minutes break. right, so let's resume our lecture. So let's talk about borrowing now that we have the ownership system. And make sure I can click here. So when you have the ownership system, what you can do instead of moving the ownership, you can borrow, right? You can borrow the ownership. This basically means I'm transferring the rights that someone else can use my item. Similar to when you have a car, you can have someone borrow your car and hopefully they use it correctly, right? And they will return the item that they borrow. To do this in Rust, you use the ampersand in front of some variable. This means that the item that you put next to the ampersand can be borrowed by whoever make that call. Right? So here, for example, I have name, right? And then I do R equal ampersand name. Now R can borrow the value of name, right? That value. So right now, if you call helper function on R, this is not okay. This is not okay because R is not actually owning the item. R is just borrowing. You are declaring that, hey, I'm going to allow R to borrow this value, and whenever R needs it, the ownership is transferred to R until R finish using. So there's a transfer of ownership right here, and then it's a transfer back, and then another transfer, right, to R right here. And if you have a helper function here that uses a string, it's fine because, well, you first need to make sure you are borrowing, right? You are borrowing the string. The transfer from R is now transferred to name, right? Transfer to name. And then transfer back to R. Close this. So this allows you to basically give the rights without deleting the item, right? This allows you to have the function call. The function call takes the ownership, return it back to the owner, the correct owner, whenever it's done. The earlier example is for the immutable variable, right? It means that if you borrow, by default, you cannot break something you borrow. Let's say you borrow a car, your friend's car. You're not supposed to modify the car, right? You're not supposed to modify the car, otherwise your friends will get pissed at you. This is the same thing. When you borrow someone's item, you cannot write to it. This is okay. Ampersand string, you print the name, print is just reading the value. This is not okay. I borrow the string, I push new string to it, right? This means that I'm modifying string. When you modify the string, you actually change the content. It means you're writing. To actually do this, you can make what we call a shared reference. A shared reference allows you to modify the variable. The next thing that I want you to be aware of is called lending. So instead of borrowing, you can lend. Lend means that I'm going to actively give the item to someone else, right? Instead of someone asking me, hey, can I borrow this? Lending means that me as an owner, I'm going to give the item to someone else. Why is it the case? Name is the owner. You say name lending the item, right? You say ampersand name. Name is the correct owner. This means that I'm going to hand over by lending this variable, parts of name, into the helper function. The second helper function, I'm lending the entire declaration of name to the helper function. Right? This means that you're giving the permission to someone else to use the data. To make it mutable, which is the shared reference, to make it mutable, you just put in the keyword MUT, which is standing for mutable, to make the item mutable. Over here, let mute name equal something. It means that I'm gonna allow whoever. First of all, I'm gonna allow name. This data is going to be declared as mutable, and then when you do mute, it means that name can be also modified. So you can have the update function, something like this. Push string, right? Make sure you also need to make sure you put the keyword here. So basically, you have to be careful to put the keyword mutable everywhere that matter. So don't put it everywhere. Put it everywhere that matter. The reason why you don't want to put it everywhere, period, is this is slow. Right? You can't do things in parallel if they are mutable. There are 3 types of ownership. You can be the owner. The owner has full control. Whenever you finish using the data, it's free. You can have the shared reference. The shared reference means that you have multiple readers, but no writer. Something like ampersand string, it gives the ownership to someone else, but no one modified it. This has performance benefit in terms of parallel programming. You can have mutable reference, no other reader and one writer, but the value is still shared. This mutable, right? These create serialization, which means that you cannot parallel the process of writing. You can't have multiple people modifying some shared content in detail, in parallel. Another thing I need to talk about in Rust before we move on to the algorithmic side of parallel programming is how Rust deals with dangling pointers. Right? When you have a compile time, read and write locks, so the shared reference to X, right? The shared reference to X, it means that I'm going to apply read locks to X. No one can read it for a shared reference to it. No one can write to it, my bad. Everyone can read from it, but no writer. No writer. Why is this okay? Why is it okay for me to allow everyone to read the value if I can assume no one is going to write or modify the value? Okay, let me go back to, because there was a question about can we update name without ampersand X? So is it over here, right? Is the question on this slide? Okay, so can we update name without the ampersand, right? Without this ampersand, oops, on my bad. Without this ampersand right here. Is that your question? Okay, the ampersand means that I'm gonna take the ownership, and this means that I'm gonna take the ownership, and this is mutable variable. So if you don't have the ampersand, it means that I don't have the ownership. I can't do anything with it. Basically, that's why you need to put the ampersand in. So does that answer your question? Okay, awesome. So when you have a shared reference to X, it means that if I have a, let's say, a linked list, right? Because no one modified the content of my linked list, as many people can read that linked list as they want. They can do this in parallel. Because you can assume the content will be the same. If you have a mutual reference, this means I'm going to apply write locks. It means that no other people can read or write to it. It means that if I need to modify something, no one else can read from it. It means I cannot run this in parallel. So this means write locks to X. So this is Rust solution on to dangling pointers. If you have read locks, everyone can read from it. No writer. If you have a write locks, no one can read, no one can write except for the exclusive owner. So how should I fix this code? Can someone take a look at it and tell me what is wrong with the code and how should I fix it? This is from the concept of ownership. Yep. So buffer is not mutable. So when you borrow it, you need to borrow mutable variable, but otherwise you can't push the string, right? So that's it. This is simple. So what's wrong here is my bad. What is wrong here? Oh, so this create a string, this entire string, and what it's from. Let me double check. Wait, what? So let me get back to that question. I'm not sure what would be the key differences, actually, because it seems to be like I'm gonna take that literal string and I'm gonna generate a string. So I'll get back to you about what is the difference with format and form from. Is that okay? Because to be honest, I'm not sure. Oops. I think I might have accidentally unshared the screen. To see the screen again, sorry. So do you have to use ampersand mutable? Even if we use mutable before the variable name, it depends on actually this because Rust everything is really explicit, right? It depends on what you want to do with that particular name that you just declare. If you need to modify that, you need to put in mutable. If you don't need to modify it, you just do ampersand. You borrow and you say, hey, I don't need to modify it, so I don't put in MUT. So the answer is it depends on what you want to do with it. Essentially, if you want to modify the content, you should put in the keyword mutable. So over here, the problem again is because mutability, right? The slice here, this seems okay because look as if it's okay because you're just printing out the slice, just printing out the slice, and buffer is already mutable, right? Buffer is already mutable. The problem is you're trying to push, right? S, what is S? It's a string, right? It's a string S, but then you declare saying, hey, slice over here is read only, right? No one's supposed to modify this while I'm using slice. No one's supposed to modify buffer when I'm using slice. because I just want to print it. But then in the middle, buffer is modified. Do you see the problem? Basically, this slide assume that, hey, whatever buffer between I to the end of the buffer, right? This gives you a fraction of the buffer that includes the last element of the buffer. I give the ownership to slice, and slice doesn't really modify anything, but then you change the content of the buffer. When you need to change content of the buffer, this should be write lock, right? This is write lock. It violates our assumption that, hey, at this point, no one's supposed to modify anything. So that's a great question. So there's a question about, like, are there a lot of situations where we explicitly need to pass mutable rather than keeping it immutable and return a new value function programming style? So not a lot, to be honest. Actually, there were a lot of papers that eventually they say, hey, a lot of things are basically just need to read from it. So you have a program, you write a program in a way that there's a quick phase where you modify the content. Once you're done, everything becomes read locked so that you can run things in parallel. You assume no, this fraction of the code, that a big fraction of the code, no one modified the content, and you run things in parallel. So you really, really want to squeeze out the performance, you should kind of write the program that way. All right. So another thing I want to basically point out is the try macro. This is try catch essentially, right? So from this code, let's say do something and you return the okay or error. This code is kind of tedious, right? You can basically you need to kind of like make it okay and error for each of the cases. You can use the try, which is try catch basically. Try to do the subcalculation and it will automatically generate the error if each of these function call return an error. So these are kind of like quick caveat that maps with what we learned in the option inside Scala. So you can do error and okay, and to make it a little bit more compact, you can do try question. Try question because okay would return error, like error of something like this, error message. So you can basically do this. Okay. This is similar to try catch in any other language. In class exercise 12, so you can do it at the end of this class. I'm gonna move on to the next part of the lecture. Now that we're a little bit behind. So if you go to Canvas, and don't worry about in class 10 and 11, you might have noticed that on Canvas in class 9 and then in class 12. Because if you remember correctly, we did in class 10 in class, like during the class. So everyone got that perfect score already. You don't have to do it. In class 11, if you don't forget it yet, basically, please go install Rust. So I assume that if you do the assignment, that I'm going to release over the weekend. If you do those assignments, you should have Rust installed already, but it's going to be based on Rust. All right. So let's talk about one of the key things we should learn from this class, parallelism. Right? How to make sure that you design something that can run in parallel. So as I said earlier, parallelism means that you do multiple things at once. This is basically simultaneous execution of computation, right? And this computation doesn't have to be related, but it can be related. And example warning, some examples here are in C++, because there's another really popular parallel program libraries called OpenMP that you can use and run, right? And this would be in C++. Rust, inside Rust, there's a parallel construct called Rayon that you can enable parallel programming. Concurrency is a little bit different from parallelism. This is handling multiple things at once. The things that computer do concurrently should be independent from each other. Concurrency is like process of really running things in parallel in hardware. Okay? So we kind of covered this during the future and promises. Think of Amdahl's law. Here's a block in from the Go language, the language invented by Google. That is really friendly toward parallelism. And there's a blog post that talks about this video actually inside a blog post about the fact that concurrency is not exactly parallelism. Okay? There's some caveats, some differences, and you really, really want to have concurrency. So one thing you can do in the language C is you can use this library called Silk. One other thing I need to tell you, Silk is not really supported right now by the current generation of the Intel library. So they did deprecated the support. If you want to use Silk, you need to do a little bit more steps to install them. But you can do parallel for loop. If you have a code like this, B of I equals A of I plus 1, one thing you notice is you can do every single iteration in parallel, right? You can do B0 equal A0 plus 1. You can do B1 equal A1 plus 1. You can do B2 equal A2 plus 1. Why can you do this in parallel? It's because the next iteration of my loop has nothing to do with the earlier iteration of my loop. Every single one of these iterations can be done in parallel. This is the paradigm. Basically, this is a style called parallel for loop, right? And you can do silk underscore for to make sure that the processor will take the code inside each of these loop iterations. They will actually assign them to multiple processors and run in parallel. You can use OpenMP annotation as well. So you can do sharp pragma and OMP for. It means I'm going to do parallel for loop, and it would take this code. Each iteration is assigned to one different processes and run this in parallel. Quick thing is, as I said, there's no dependency between each iteration. B of I doesn't depend on B of I minus 1 or A of I minus 1. Right? Actually, B of I doesn't depend on B of I minus 1. That's the only requirement on over here because A of I right now, the code is not modified anyway. Right? It's read only. Any question? Sorry. Any question about this parallel for loop? Thank you. All right, so another style of parallel program is called fork and join. Right? If you have a double bar here, double bar B, it means that A and B can be run in parallel. So in Rust, you can actually type this. Rust would know this symbol, and it would actually fork the processes, fork the computation into two different branches. Each of the branch should be run in parallel. A and B will be run in parallel. So you can use Rayon. This is Rust. This is basically this code is written in Rust. So if you want to do Fibonacci, right? What you can do is basically fib of n minus 1 and fib of n minus 2 can be done in parallel, right? You call two functions. You already know n minus, well, you already know n, so fib of n minus 1 is say fib of 5, fib of n minus 2 is fib of 4, right? So you can do this. I will fork out fib of n minus 1 over here and fib of n minus 2. Make sure I compute this in parallel. Then I'm going to join them later. How do I join this? Basically, because I do pattern matching, right? X is going to equal fib of n minus 1, y is going to equal fib of n minus 2. then I will return x plus y, right? Then I'll return x plus y. How does this execution looks like in a data flow, right? So you have fifth of n, which will be run in parallel by forking fifth of n minus 1 and fifth of n minus 2, right? Which will then fork fifth of n minus 2 and fifth of n minus 3, okay? The fifth of n minus 3 and fifth of n minus 4. This is a great question. What's Rayon's function? So Rayon's that's actually quite a bunch of things that Rayon can do. So I would definitely recommend you to check out the Rust documentation, because Rayon is anything to do with parallel programming in Rust. The common one would be parallel for loop fork join. So there'll be a few examples on that, and the rest you can check out the document on Rust on what else Rayon can do. And if you have questions, please feel free to ping me, and I'll answer those. Is it worth it to use dynamic programming for parallelism with parallelism? Yes. The answer is yes. Memoization is also another powerful tool. One thing about memoization is you're writing things to the table, right? So you need to make sure the writer, like you need to make sure you manage who write to what part of your data to actually enable parallelism. And yes, the last comment is also great. Does it mean we're doing fifth of n minus 2 twice? Yes. That's why if you can do dynamic programming on top of this, it can be a little bit faster. Actually, quite a lot faster, because you don't have to recompute fifth of n minus 2. Yeah, if you keep the last two elements in the table, then you don't have parallelism, because you then require that the only two things you can remember is fifth of n minus 1 and fifth of n minus 2. You can't just say somehow there might be some forking out where you need to compute f of n minus 1 and f of n minus 5 and f of n minus 7, right? Do we need to use memoization here? Then it depends. Oh wait, you can, but with memoization, you need to explicitly tell which part of the memoization can be written on. So you need to make sure you manage the ownership. Because if you don't manage the ownership and you use Rayon, Rayon will not parallelize that for you. Because if Rayon see mutable, they'll do that in like serially. They won't do that in parallel. All right. So the next concept I want you to introduce. Can you actually write an example of DP in Rust? Maybe let me write a. I need to think of a good example. So let me do that next week. Is that okay? All right. So that's my homework. I'll do it next week for you. I'll have an example of like dynamic programming in Rust. So nested parallelisms combine basically parallel for loop and fork join, right? So over here, if you look at this computation graph from top to bottom, right? What's the maximum of concurrent computation that I can get out of this parallel task? The answer is basically if I draw the line right here, right? I will see that there are at some point 7 things I can do. 7 things I can do in parallel. Parallel task means that with this dependency graph, 2 tasks are parallel if there's no path. If there's no path between each other. So if you look at this task graph, the number of concurrent operations, you look at that line where there's no path 32. That's the maximum number of concurrency. So that comes to our kind of like the last concept that I want you to learn today, the cost analysis. The cost analysis. This is a little bit different from the big O notation that you love from the algorithm class, but it's kind of similar. So we would first define work as the number of operations, right? And we would define depth or the span as the longest chain of dependency. Longest chain of dependency. The difference here is the depth. The depth talks about how many things are the serial portion of your code. The parallelism is work divided by depth. Work divided by depth. This determines the number of processors that can be effectively used. If parallelism is 1, it means that I just need one processor. If parallelism is 4, then it means that, well, if you have 4 processors, you can use all 4 of them. Right? Remember the Amdahl's law. You want to make the program as parallel as possible. Well, and then if you hardware and system researcher like me, right? If consumer buy a multi-core CPU and I have a program that's not really parallelizable, what else can I do? I can run other program. I can turn off the processor. I can literally do that. Save power. I can actually use other processor to help the single thread first processor that's running something. So if you're curious about this, let me know. There are actually some other hardware ways to like make the serial portion fast. But let's go back to the content of our class. Let's go through this example, right? I want to do a sum, basically. I have an array. I want to add every number together. This is a sequential version of my sum. Total is mutable. Right? Start with 0. This is my input. It's an array that consists of multiple integers. I'm gonna take a look at num in V. This is our array. Total is going to be total equal plus total is going to equal total plus num. Then I return total. Any question about this code? Basically, this is really, really simple. I go through all the elements and I add everything together. Right? Oh, what's 0 before I32? It means I'm going to have value. This is the value 0. 0 type I32. So what's the work of this and what's the depth of this? If you want to add n items, the work obviously is n. Depth is also n, right? You need to do it one at a time. So parallelism is 1, n over n, right? Next example, parallel version of my sum, which will use Rayon. The way this works is I have parallel sum, same input, our array, right? This is if the length is less than 1, you just return V, the sequential sum of V, which is basically that element. Otherwise, I will have a split, right? You split the array, by the length, you split that in half. I have the left side and the right side. I would use Rayon fork join right here, right, where I will compute left sum and right sum by recursively calling this function in, right, the parallel sum will get recursively called. I will add the left side and I'll add the right side. Then I'll sum them together by returning left sum and right sum. What's work and what's depth of this? Basically, this is what I would do, right? Oh, my bad. Join is only once. You see join twice, it's basically, I'm gonna say I want to use Rayon join library API. This is not using join, this is declaring I need to use this API. Then the actual join is the next one. All right, so the work obviously is still n depth. You go half, 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 right? So your depth is actually log of n. So there was an answer on span of n over 2. Yep, it's log of n. If you divide things by half every iteration, that's not n over 2, that's log of n. So your parallelism is n over log of n. Right? This is good. Actually, this is actually good parallelism. So why this cost model? These are simple, right? You just need to draw the dependency graph and that's it. There's a theorem called Rent theorem, where if you have P processor, you can make a scheduling in order of work over parallelism plus depth. Right? This, if you look at this kind of follow the Amdahl's law. Why is that the case? Depth is the zero portion. Right? Depth is a zero portion. This also can dominate the time. The lower bound of how much time do we need if we have P-processor is basically the depth or the WOP, work over number of processor. So when you want to design a parallel algorithm, right, basically what we call work efficient, which is kind of like a good enough bar for writing a parallel program, right? The work should be roughly the same as sequential running time. Why is that the case? You're not adding too much extra work so that you can run parallel program. And a polynomial parallelism, like n of 1/2, is generally good. N of 1/2 is generally good. So if you got something around this, good enough, fast enough, essentially. So let's go to a not really good example of Quicksort. How many of you don't know what a Quicksort is? Okay, so because there's no answer, I assume everyone know about Quicksort. You forgot. That's fine. The way Quicksort works is I start with an array, and then I pick some random value. I'm gonna compare everything here in my array. If it's less than the value I pick, the value that I pick, which is well p, right? This is the same as p, basically the pivot. If it's less than this, I'm gonna put in the one side of my array. If it's equal, I'll put on the middle side, and if it's greater, I'm gonna put on the right side. Then I'm gonna do the same thing on each side of it, left and right, right? Left and right. So this is the everything that's smaller than p, and this is everything that is greater than p. Everything smaller than p go to one array. Everything that's greater than p go into another array. Everything that's equal to p stay in the middle. You don't have to do anything. Then I'm going to do a parallel quicksort on the smaller one and the greater one. The smaller one and the greater one. Right? Then I'm going to append, right? Append the sorted version of the smaller array appended by the middle part, appended by the greater part, and everything will be sorted from lowest to the highest value. So if you look at this algorithm, if you look at this code, basically, we use a parallel program, right? You parallelize them by splitting them in half. So you have the big array here. This array gets split into a small array, right? Which gets split to another small array. Right? You can use rayon join as well. It's the same. Right? Basically, you are branching things out and then merge everything back in. Right? This is fork join. It looks okay, right? It looks relatively okay. What's the work and what's depth? So let's do consider that example, right? Partitioning, breaking things into 3 different arrays, is done in all of. My bad. Let me move this here. Partitioning and concatenation, breaking things down, is done in O and work, log n of depth, right? Log n of depth, which looks okay. The issue is, oops, the recursive call is done serially. Why? All those compare. If you look at this, all this comparison, this is done serially. Right? This is a serial part of your code. So that dominates your complexity. Right? So if you try to draw the dependency graph, it's going to not be really good. And I'm going to draw it with this slide. So it's basically a blank slide, right? The comparison is sequentially done. You first compare n things, then you compare again. Compare in this step. Just again compare n things, right? And then you break it down again. This is again compare n things. So what happened here? Can you compare these n things in parallel at once? So I'm just really asking you this one question. Why can't I use parallel comparison? Am I writing something to my array? No, right? It's read only. Are you all with me? Basically, this comparison, the original array I'm comparing to is read only. So I can do this in parallel, right? So why don't we do this in parallel? The answer is yes, we should do that in parallel. So this is the zero portion of the code. We assume this partitioning doesn't often work, log n, but the complexity is still work of n log n, depth of O of n. Depth is O of n. Depth is O of n because you have that recursive call. This is actually what happened, right? You do the comparison, and this is done serially. You need to. This is split number 1. This is the second split for the other 2 arrays, right? And because each of these steps is serially called, right? You finish the first part, then you call the second part. The second part will have its own like sequential call. So this is a really good parallel algorithm. What you want to do is the recursive call should be done in parallel, something like this. When you split, it should do both of them. It should do both of the calls in parallel. The parallel partition is fine. If you partition things in parallel, you merge, concatenate things in parallel. You also should call the function in parallel. Over here, your depth is log square of n. So this is kind of like, it's not log of n because it's log of n multiplied by log of n if you know the big O of the Quicksort. This is where the comparison comes into play. This comparison that do in parallel at this part is O of log n. So in total, basically you have O of log n multiplied by log n. That's why it's O of log n squared. Because each step here is O of log n. Work again similar in log n. Now your parallelism is n over log n. Yay, better. Right? This is a better parallel program. This is the same slide as earlier. Work is O of n log n, and span is O of log n squared. So that kind of summarizes the work and span of a better version of Quicksort, which do this. You parallel partitioning part, calling part, and this allows you to call the two functions in parallel, which is the fork join parallelism plus for loop. It is just nested parallelism, essentially. Then, right, to design a good parallel program, there are, aside from rayon fork join, there are three things that I'm going to introduce to you: map, reduce, and filter. Right? So let's actually wrap this up because it's actually getting close to the end of the lecture. So that I mean it's getting close to the end of the lecture anyway. So we can wrap up earlier today. In terms of these operations, one thing you've noticed, this is done on a collection. What is a collection? Array, vector, list. So these are all collections. From scalar days, back in the first half of this class, you can apply map, reduce, and filter. And these are really, really good constructs. Why are they map? You apply F to every element of my collection. This can be done in parallel. Reduce, you combine elements in a pair, which means that this can be done in parallel, pairwise comparison. Filter, we change an element if this function returns true. The actual check can also be done in parallel. So everything here, every operation here, map, reduce, and filter are friendly toward parallel program. So here's the map parallelism. You want to apply a function on every single element. What is the work and what is depth? So let's say I have n elements. What's the work and depth of map? It's yes, it's constant depth of n for work 1. So the parallelism is n. What about reduce? This is reduce operations. Right? Map is a little bit simple. Map is really simple, so I didn't draw this diagram. This is what you do when you have to do the reduce. What is work and what is depth? Then you have a tree-like structure like this. Log n of depth, yes. What about work? of n. Right? You do a pairwise operation, so depth is linear. So parallelism with n over log n. This is another good parallelism that we can get. What about filter? Right? So filter is a little bit interesting, where the major challenges are you need to figure out how many are selected and how to retain and output that, right? So this depends on how you design it. This depends on how you design it. The complexity depends on the element that you're being filtered. So you can basically, the way to do this is one way when you design an algorithm for a filter, you convert this with data flow graph. If it looks pretty linear, that's bad. You want to make sure they look as parallel as possible. And here are some example of map. Right? So now that we talk about the map, filter, and reduce, let's talk about examples. Map in Rust, you do fn map. F is a function, or is an element that you want to map. Self here need to be iterable because you are dealing with collection. The operation is on F, right? Let's say you want to do fifth of 1 to fifth of 100. Fifth of 1 to fifth of 100. One thing you can do here is you first have fifth of 1 to 100 parallel iteration. N goes in as an input. The function is I'm going to compute fifth of n. Fifth will be a function that I defined earlier, which is f of n minus 1 plus f of n minus 2. Then you collect to generate the array. Okay. What else do we need? Well, we do fork join. So you do rayon join fill n minus 1 and fill n minus 2. Oops. And this is it. Basically, now you have a Fibonacci. You fork join n minus 1 and n minus 2 branch, right? You iterate this in parallel. Using parallel iterator, you map n as an input to call fib of n. Everything from this is basically array, right? That consists of 1, 2, 3, 4, 5, blah blah blah, 100. Then you apply fib of n. So every element is now fib of 1, fib of 2, blah blah, fib of 100. Okay? So the actual applying the function, it depends on how long Fibonacci takes, but over here it can map Fibonacci function to all the arrays. Okay. All right. So how about reduce? Let's say we want to do parallelism. Again, back to our basic example. Here is how you can use reduce for parallelism. Start with the elements 1 to 5, no, 50 million, sorry. You start with 0. You add a and b. Basically, this is our function. Basically, if you want to make this anonymous function in Rust, you can do this. Vertical bar, input to my function. Whatever comes next, this is the function body. So if you look at this part, it's a function that takes a and b and then return a plus b. The vertical bar signify these are the inputs. What comes afterward is my function body. And I am going to basically add by performing a reduce, starting with 0, add a pairwise element from 1 to 50 million. I have a code for parallel merge sort. This is from last year, last 2 semesters. My bad. I'll put the code for parallel merge sort on a slide next week. We'll go through that example. Last 2 semesters, there was a student that wanted to do parallel merge sort for his project. So I'm like, okay, I can't give you that example because this is one of the student projects. So we'll go through the code for parallel merge sort next week. Is that okay? So this can be adapted to perform parallel merge sort. How about filter? Let's say I want to filter out the number of primes. I want to get a collection of prime number between 1 million and 20 million, which is actually really computationally expensive, right? One thing I can do is first I have a function called isPrime. This basically take one input, then check if this is prime number. The way I can do this in parallel is I use parallel iteration by applying the filter function. Filter function take n as an input, then it called the isPrime function here in parallel, and then count the number of true. Count in the number of true. Dot count means I'm going to count the number of elements in that array. So this is how you can use filter in Rust. And before we leave today, right, next week we will focus on, now that we know the more like a theory side of things, let's put that in practice. So we're gonna do more practice. We are going to do more about, be careful about these things because these things are not exactly friendly toward parallel program. Ask this question. Parallel programming seems good, but what else can serialize your program? Okay. How about when data is being shared? How about data is being shared and modified? Right. So think about it going into the weekend. Again, because I realized we just had an exam, so I don't want to like overload everything in this lecture, and I also realized only noon. But that's basically almost the end of our slide deck here. The last example that I'm gonna show you is, how many of you took OS before coming into this class? Because I want to ask a few questions about one of the assignments. Why are you here? So for those of you who take OS before, because I know some of you do, how long does it take for you to take to finish the thread pool assignment? Long time. Okay. So if Vicky say it's a long time for him, it's definitely quite a long time, right? And that's a good reason for that, because basically on the OS side, you need to actually make sure a lot of things are done correctly. I'm going to show you a sample code for how can we create thread pool in Rust. So give me a few seconds. Okay. All right. Do you see my code? Hello. Do you see the screen that show the code, and can you read the? Okay, perfect. All right, so thread pool is a concept where if you have parallel program that has multiple tasks, that each task can be done independently. There's a concept in computer system where we can create this pool of worker threads. The way worker threads work is it's kind of like having a worker in a company, right? Each person can go and grab some work and they do that work. When they are done, you go and get another work and then you finish it. This is the concept behind thread pool. Each thread would go and get a task run the task, finish the task, and then get another task, run the task, finish the task until every single task finished. Inside the thread pool, you basically have any number of threads like this, any number of threads. Right? Then you use the Rayon library to build a thread pool. So here, you start building a bunch of threads. And this is assumption. Basically, this configurable. Let's say there are 30 tasks inside my thread pool, right? Here is the policy. Basically, I'm going to apply the policy on my thread pool, right? By first, I'm going to spawn a task. I'm going to spawn a task. Then over here, basically, I'm going to pick a random policy. Each thread inside my thread pool will go and pick a random thread that can be executed on my processor. So this is just the random number. Simple enough because I don't need to have a complex policy. The policy that go into the thread pool can be really complex based on what you want. Random policy is pretty bad, but it's simple. Then the scheduling policy over here is when I run something, when I run this random task, I'm going to run it for a random number of times between 50, I think, millisecond to 1000 milliseconds. Then I'm going to switch it to another task because you have short concentration. You do things for only a short burst of time, and you wait for you're going to switch to another task. After the allocated time, I'm going to sleep. Basically, standard threads allow you to sleep. Hey, I'm not going to do that task anymore. I'm going to switch to another task. And this can be done basically using Rust and Rayon and the standard library. Now you have the thread pool here, right here is a thread pool. If everything finished properly, you return okay, everything finished running. Yay, that's it. Any question about this code? It's so quiet, so I assume there's no question about the code. So that's basically the note here. As I said, the random scheduler and random duration is generally bad, so you might not want to use the policy in real life. Because think of it this way, this is the reason why the policy can be bad if you do it randomly. Let's say you want to go shopping, right? And there's a long line of checkout. Then the manager comes in and say, hey, I'm going to pick whoever gets to check out, I'm going to pick it randomly. And you can only check out for a random amount of time. Then I'm going to switch to someone else. So this is basically bad for all the customers. There's a big design. This obviously this is better than sequential execution, but this is a really, really big area in our systems on how do we make a good policy. That's it for the class today. Any questions before we kind of like wrap it up? Basically, that's it for the class. One thing left is for the in-class exercise 12, which both of the codes are on Canvas. Finished really early today. So any last minute questions? So first of all, I still owe you the example for memorization. in Rust. I owe you the merge sort example, which we'll both cover in the next week. And then I'll continue on into parallelism, how to do parallel program in Rust, and how to do parallel program in things like OpenMP, and what are the other types of parallel programs. Once we are done with those, we will go. So pick both of them. The exercise is basically for you to play with Rust, because I'm pretty sure last time when we say install Rust and play around with it, most of you just install Rust and print hello world, right? This one is going to be a little bit longer code. By longer, a little bit longer, it's definitely less than 50 lines of code. I'll let you try it out, and then whatever compilation error you got, try it out from what we learned today first, and see if you can get it to compile and run. If you cannot, if you spend maybe like until the end of this class period. So one quick thing is, I'm actually on a vacation right now, so I'm gonna leave things a little bit earlier for you guys today. But if you have questions about your in-class exercise, please just put it on Discord. I'll come back and address those as soon as possible. No, don't worry. So yeah, so the in-class exercise is basically, now that you have Bus installed, basically try to run it. Try to measure it runs based on things like mutable, the ampersand thing, the ownership thing, and the data type. And I think that's pretty much all the tasks that I put in. Yeah. So that's pretty much it for this class. Thank you so much for joining into our lecture. And I'm going to post the video recording whenever WebEx give me that.